Instituto de Ciencias Matemáticas in Madrid, and she will talk on quantum conditional relative entropy and quasi-factorization of the relative entropy.
Yes, perfect. Thank you very much. First of all, thank you to the organizers for organizing this very nice workshop and for having me and my talk here. I'm going to talk today about a concept that we've introduced that is called quantum conditional relative entropy, and how we use this concept to prove results of quasi-factorization of the relative entropy. This is based on a couple of papers that have these references on arXiv, just if you want to check them. And this is some joint work with Angelo Lucia from the University of Copenhagen and my supervisor David Pérez García from Universidad Complutense de Madrid. So the idea for the talk is going to be the following. I decided to separate it in a couple of parts. In the first part, we are going to present some things that are mostly related to quantum information theory. So we are going to focus most on this kind of settings, and this is where we'll introduce these concepts and these results of quasi-factorization. And in the second part, we will see how these results can be motivated in a quantum many-body system, and how these results can be used in this setting to prove interesting facts. So let's see. First of all, we can see that this problem, this result of quasi-factorization of the conditional relative entropy in the quantum case, can be motivated from an analogous result of the classical setting of classical entropies. So when you consider classical entropies for a function in a probability space that you can define like this, you can also consider a sigma algebra inside the sigma algebra contained in the sigma algebra of the global space, and you can define the conditional entropy of a function in this form. So the global entropy is the measure of the function log of the function minus measure of the function log of measure of the function, and the conditional entropy is just to condition each one of these terms to the sigma algebra. And when you define these concepts in classical settings, there is one result from 2002 from Daipra, Paganoni, and Posta, where they prove what you can see here, which is basically that you can upper bound the entropy of a function by the sum of two conditional entropies defined like this in two sub-sigma algebras of the global sigma algebra and a multiplicative error term. And the idea of this multiplicative error term is that in general these two sub-sigma algebras don't need to be independent under the measure that you're considering in this probability space. So you have to find a further measure that makes them independent, so that the first one is absolutely continuous with respect to this one, and they have the same marginals. And when you do that, then you get this multiplicative error term, where this h is the Radon-Nikodym derivative of the measures. So if you consider the first measure, and for this measure, these two sigma algebras are already independent, this error term disappears. And then you just get an upper bound for the entropy of a function in terms of the sum of two conditional entropies. So now, this is what motivated the idea of trying to prove something similar for the quantum case. So let's see how we can translate this. This is what I just showed in the previous slide, and this can be translated to the setting that you see here. So you can consider a tripartite Hilbert space, two states in this tripartite Hilbert space, and then the idea is that we would like to prove something like this. So an upper bound for the relative entropy of these two states given by the sum of two conditional relative entropies, which is something that we still don't know what it is, and a multiplicative error term. And this error term should measure somehow how far the sigma algebras or conditioning here and here to these two subregions, how far they are from being independent, let's say that. So this is something that we will see during the talk, how these two concepts can be defined and how these kind of results can be proven. So this is the idea. Well, it's clear that the first thing that we have to do is to define this conditional relative entropy. And to do that, we first go to the quantum relative entropy, that is perfectly known. So when we consider two states, the relative entropy of these two states is given by this expression, and it satisfies many properties, but some of them in which we are focusing are these four ones. So the property of continuity with respect to the first state, the property of additivity for tensor products, the property of superadditivity when just the second state is a tensor product, and the property of monotonicity or data processing inequality with respect to quantum channels. And we are focusing on these four properties because there's a result that characterizes the relative entropy in terms of these four properties. That says that if you have a function that satisfies these four properties, then it's the relative entropy or a multiple of the relative entropy. And it's a result of Wilming, Gallego, and Isert, but it's mainly based on a result of Matsumoto of 2010. So the idea is that we want to do something similar. We want to provide a concept of conditional relative entropy by providing some properties that it should satisfy and try to characterize the form of this concept. And this is what we do. So going back to the classical case and see what it means to have a conditional entropy in the classical case, and taking into account that the conditional relative entropy in A for a bipartite space should be something that should provide somehow the measure of the relative entropy of the global system conditioned to the measure of the relative entropy in the complement of A, these properties are reasonable, taking into account these ideas. So the first one of them is the continuity property, which comes directly from the idea that when A is the global system, this should extend the relative entropy itself. The second one is a property of non-negativity, and this comes mostly from the idea that it should extend the classical concept, and in the classical concept this always happens. And also it has to be zero if and only if you can recover rho by means of the best recovery map for the partial trace. And this is something that we impose because we want to have some conditions for the results that we want to prove after that for the quasi-factorization things of the relative entropy. After this, let's take into account that the conditional relative entropy in A has to be somehow similar to the relative entropy when you consider the two states with support in A, and it should also measure the correlations with these states with the complement with B. But in particular, it should satisfy, at least in A, the properties of additivity and superadditivity that the relative entropy satisfy. So this is why we impose these two conditions. And finally, remember that in the case of the relative entropy, we needed to say something concerning quantum channels. So this is more or less what we are doing here. But now it's clear that if we consider a channel that just acts on B, for example, it shouldn't decrease its quantity because of the idea with which we are trying to define this concept. So the point is that if you consider just a channel that acts on A, it's reasonable that it decreases its quantity, but in general, for a general channel, you should also add the effect of the channel in B. So given a channel, you need to trace out the part in A, and then you need to consider the conditional relative entropy in B, and when you add this effect to the relative entropy, the conditional relative entropy in A with the channel, then you get a data processing inequality. And this is what we impose to get the definition of the concept. And now, if you consider these properties, you can notice some facts. And some of them, for example, are that if you consider the sum of a conditional relative entropy in A and B, it satisfies certain properties. The first one of them is continuity, which is the same that for the relative entropy. The second one is additivity with respect to tensor products. And the third one is superadditivity. So, of course, this can't satisfy the property of monotonicity, because if it did, if you go back to the characterization of the relative entropy, it would be the relative entropy, and we don't want that. We want something different. But even though for these properties that we have defined in the previous slide, we can prove that the only possible conditional relative entropy is this quantity here, which is the relative entropy in the global system in AB minus the relative entropy in the complement. And this is the only possible definition for this for this quantity, which is something quite interesting. But of course, we were looking for this definition because we wanted to prove results of quasi-factorization of the relative entropy using this concept. And if we are not able to do that, then it's not the best definition for us. So now the question is, if you consider a tripartite space ABC, and you consider AB in one part and BC in another part, can you prove something like this? So can you prove an upper bound for the relative entropy in terms of the sum of these two conditional relative entropies and an error term that measures, in this case, how far sigma is from being a tensor product between A and C? And well, the answer is yes. So this is what we did. We proved this result. So where we get exactly that bound that I was mentioning before. And here, the multiplicative error term is 1 over 1 minus twice this norm of this quantity. And this quantity is exactly something that can measure how far sigma is from being a tensor product, because if sigma is a tensor product, then this is an identity, so this is 0, and this quantity is just 1, so there's no error term. And if you remember what I mentioned in the beginning of the talk about the classical result, it's exactly the same. So here, well, you know, here for H we already consider the difference with the identity. Here for H they just consider the Radon-Nikodym derivative, but except for that, the idea is exactly the same. But this result is also nice because of another reason. Because if you rewrite everything, so this is the inequality that we had, and now if you introduce the definitions for the conditional relative entropies, then just by doing some algebra, this inequality is equivalent to this one. And from here, you can see here that these states have still support in ABC. From here, you can go to this inequality, which is also equivalent, just by in one direction is just considering that HB has dimension 1, and the other direction is just data processing inequality. So what we can see is that our result is equivalent to this inequality. And this inequality, if you remember some properties of the relative entropy of two states, one of them that is superadditivity, that says that if when you consider here a tensor product, you get this upper bound for this quantity with a 1 here. And also, if you remember monotonicity, that says that every time that you apply this quantum channel, you cannot increase the relative entropy. If you apply monotonicity twice for both the partial trace in A and B, you get here an inequality with a constant 2. So you can see that in our case, our result is something that is universal for sigma, it's not just for sigma a tensor product, and gives you a constant here, well, a measure here of how far sigma is from being a tensor product. So of course, if this term is very big, if it's bigger, greater, everything here is greater than 1, of course this result is worse than monotonicity, so you just stick with monotonicity. But when sigma is close to be a tensor product, this is an improvement of the inequality that you could get for monotonicity, and therefore is kind of an extension of superadditivity. And also, it's interesting to mention that when we were defining the conditional relative entropy, we wanted to extend the classical concept of conditional entropy of a function. So something that we have to check is that we are actually extending the concept. So if we go to classical state, we need to recover the classical definition of conditional entropy. And this is something that you can see here. So if you consider the relative entropy of two states and the conditional relative entropy that is just below, and you consider that these two states are classical, then just by defining every observable FAB as the gamma operator for sigma AB of rho AB, which is basically sigma AB minus 1/2 rho AB, sigma AB minus 1/2, and the same just for B, then you can obtain these two expressions here. And with these two expressions here, if you identify a measure in the classical case with a trace with respect to sigma, and also you consider that conditioning to a sigma algebra in the classical case is the same that tracing out just one part, then you recover exactly the definitions of the classical case. And also in the classical case, if you define if you take that every observable is just a Radon-Nikodym derivative of measures, you can recover the concept of relative entropy of measures in the classical setting, and then just by identifying every measure with a state here, you can recover the concepts of conditional entropy and quantum conditional relative entropy. Let's say that. So good, so far so good. So the idea now is that I'm going to show a brief sketch of the proof of this result. And it's just because I think that some of the techniques used here are interesting. So we divide the proof in 4 steps. And the first step is just some algebra. So the idea is that we show that when you have a relative entropy of 2 states with supporting AB, you can bound it by the sum of these 2 relative entropies in A and B, and an error term that is the one that we are going to bound in further steps. So this is just some algebra, and this error term that we get here is the logarithm of the trace of an exponential of several things. The second step is a bit more interesting. So now we have to bound this error term, and what we get is that it's bounded by the trace of this term here, that is the one that will provide the error term in the final part of the proof, and this tensor product of these 2 difference of states. And let's see. So the first thing that we do is recall this result of Lieb, where he introduced this pseudo inversion of an operator in terms of another operator, and he proved this extension of the Golden-Thomson inequality for 3 operators. So this is something that we use because here we have an exponential of 3 terms. So we just rewrite everything, and applying Lieb's theorem, we get something like this, where this T is this pseudo inversion of sigma AB in terms of sigma A tensor sigma B. And we just add and subtract an identity here. And remember that we had a logarithm of the trace of M, so now we just use that when you have the logarithm of x, that's less than or equal to x minus 1. So this is how we get rid of the logarithm, and we just get the trace of this L, which is the difference between this T and the identity, and rho A tensor rho B. And in the second part of this step, we just use a result of Suter, Berta, and Thomas Michel from last year, where they prove that this operator can be equivalently expressed by this expression that you can see here, which is a bit nicer for us to do some calculations with it. And when you introduce this definition, you can also prove this result that says that when you introduce a sigma A or a sigma B inside the expression of the previous slide, what you get doesn't change the quantity. So this is why you can subtract here sigma A and sigma B and obtain exactly the same. And this is the end of this step. So now that we have this expression, in the third step we just bound it in this form, already obtaining the relative entropy, which is what we were looking for. So in the first part we just use Hölder's inequality to separate here an infinity norm of the term L and a one norm of the other 2 guys here. And after using tensorization of Schotten norms, we can also separate these 2 terms here in these 2 one norms. And now, just using Pinsker's inequality for these 1 norms, and using after that data processing inequality, we can just recover the relative entropy that we were looking for with a factor 2 here. And if you remember the statement of the theorem, the expression that I was giving for the error term was a bit nicer than the L that we have here, because it's defined in terms of this operator, Lieb's operator, and the identity. But after that, in a fourth step, you can bound this error term by the nicer error term that we had in the final part. And this is just a consequence of some properties of non-commutative LP norms. Good. So this is the idea of this proof. And now, once we have introduced the concept of conditional relative entropy, you might argue that, okay, we have stated some properties and we have found a quantity that satisfies these properties, And for us, it's useful because we were able to prove the result we were looking for, but it might not be the best definition that one could think about. So the idea now is that maybe by changing some of the properties that we presented in the definition, maybe we could get another quantity that would be more suitable for the purposes we were looking for or for another purposes. And if you remember the properties that we stated in the definition of conditional relative entropy, maybe the less natural one was the last one, the one concerning channels, because of the behavior that we were adding, because we were adding this effect of the channel in the part B to compensate the effect in the part A. So maybe we can just remove this property and just focus on the other ones, which are more natural, because of the idea of trying to extend both the relative entropy and both the conditional entropy of the classical case. And then when you just consider these properties, there is more space for introducing some other quantities satisfying these properties. So far, we just have one example, which is what we call the conditional relative entropy by expectations. And in this case, it's just defined by the relative entropy between the state and the best recovery map for the partial trace of the same state with respect to sigma. And the notation here of this EA star comes from the fact that it's the dual of a minimal conditional expectation. So this is also where the name comes from. And the idea, well, of course, the first property that it has is that it's a weak conditional relative entropy in the sense that it satisfies the properties of the previous slide. And you can compare both definitions, so the definition that we saw before of conditional relative entropy and this conditional relative entropy by expectations, and you can think, okay, do they coincide in general or are they different? And the answer is that in general they are different, and in general they are not comparable, so you can't always find an inequality between both of them in any direction, but there are some cases where they coincide. So these cases are quite trivial in general. The first one is that they commute and all their marginals commute. The second one is that the second state is a tensor product, and the third one is where they vanish. In this case, they coincide. But well, we also have some example that is not so trivial and is not zero, but in general, it's an open question. And for this definition, we were still looking for results of quasi-factorization of the relative entropy. So for this definition, we can also prove something like that. But now you can see that the idea is the same. So you're still getting a bound for the relative entropy in terms of the sum of two conditional relative entropies, in this case by expectations, an error bound, an error term, sorry. But this error term now is given by this huge expression. So maybe it's not really convenient for our purposes. But anyway, you can get something like this. Good. And now I will go to the second part of the talk, which is basically tell you why we are looking for this kind of results, why they are interesting. And this is quite related to the talks of Cambyse and Ivan before. So, well, let's just go to open quantum many-body systems. So let's completely change the setting. In this case, we are considering open quantum many-body systems because they are interesting for information processing. And when we consider a system inside an environment and a weak coupling between both of them, the dynamics of this system is dissipative, and its continuous time evolution, well, a continuous time evolution of a state on this system can be given by a quantum Markov semigroup, which is something that they have discussed a bit before. So just to briefly recall, if we have a lattice, a quantum speed lattice system, what we have is actually a finite subset of CD, and to every side of this lattice we associate a finite dimensional Hilbert space, which we are always going to assume that have the same dimension, so they are all C capital D. And the global Hilbert space associated to the global lattice is a tensor product everywhere of the local Hilbert spaces. So for these definitions, they mentioned something before, but the idea is that a dissipative quantum system, a quantum Markov semigroup, is a one-parameter continuous semigroup of quantum channels And I'm always going to work on the Schrödinger picture, so this is why I'm considering the star here. And the idea, I'm not going to go into much detail because they explained this before, but the idea is that if you consider a state on the system, an initial state that we denote by rho lambda, after a time t, the evolution of this state is given by the application of this channel sub t in this state, and because of the things that can be mentioned before, it can be given by the exponential of t and this generator, this infinitesimal generator that is the Lindbladian, applied to rho sub lambda. And when we assume several things on the setting, which are, for example, that it's primitive, so it has a unique fixed point that is also full rank, we get that for any initial state, there is convergence to a fixed point, to this fixed point, that we always denote by sigma lambda. So we know that there's convergence, but we would like to know how fast this convergence is. So for an infinitesimal generator, for a Lindbladian, we define the condition of rapid mixing, taking the supremum over all possible initial states, so over all possible rho lambda, and seeing after a time t when the norm of the difference between this rho sub t and the fixed point scales polynomially with the system size and decays exponentially with time. This is what we are going to call rapid mixing. And we are interested on finding examples of rapid mixing. And by finding examples, I mean finding certain dynamics and certain infinitesimal generators for which this holds. And there are many ways of finding examples of rapid mixing, but the ones we are interested on come from functional inequalities. So the idea is that if you define a Log-Sobolev constant, they call it before MLSI, you can define it by this quotient. So you take the infimum over all possible states of the entropy production over twice the relative entropy. And if you define this constant, then if it's greater than 0, you get this inequality between the relative entropy for every time t of rho sub t and sigma sub lambda, the relative entropy in the initial states, and an exponential decay with time with a factor twice the Log-Sobolev constant. And now if you put this together with Pinsker's inequality, you have this global inequality. So first, with Pinsker's inequality, you can bound the one norm of the difference between rho sub t and sigma sub lambda by the square root of this relative entropy, the initial states, with a factor 2, and the exponential decay with time and the Log-Sobolev constant. And now this relative entropy of these two states is maximal when it's the logarithm of 1 over sigma mean. So when you consider this one norm of this difference and you see that you can bound it by something that scales polynomially with the system size and decays exponentially with time, this is an example of what we have here. So this means that Log-Sobolev constant implies rapid mixing. And since we were looking for rapid mixing, we can reduce it to find positive Log-Sobolev constants because they will imply this rapid mixing. And now we have the problem of finding these positive Log-Sobolev constants, which can also be done by many procedures, but one of them is focusing on the classical case and using the results that we have mentioned before. You'll see now how. So the idea is that in general, given a certain Lindbladian, we want to prove that the Log-Sobolev constant of this Lindbladian is positive using results of quasi-factorization of the relative entropy. And the scheme that we can follow and comes from the classical setting is the following. So the idea is that you can first prove a result of quasi-factorization of the relative entropy. After that, you can use a recursive geometric argument to provide a lower bound for the global Log-Sobolev constant in terms of some conditional Log-Sobolev constant. And finally, if you are able to prove that this conditional Log-Sobolev constant is positive and doesn't depend on the system size, then you get that the global Log-Sobolev constant is positive. This is what they use in the classical case, and this is what we try to use in the quantum case. And this is why we try to prove results of quasi-factorization of the quantum relative entropy. This is the whole motivation. So once you see this scheme, the idea is, okay, so have we managed to do that so far? And as Ivan mentioned in his talk, this is the truly open problem that he was mentioning, so far it's not easy to use these kind of techniques for that. But we can use them for a very specific case, for a very particular case, which is heat bath dynamics with product fixed point. And using these techniques, we can see that it has a positive log Sobolev constant. So the first thing that I was mentioning in the previous scheme, which was the quasi-factorization, in this case, is given by this inequality. So you can see here an upper bound for the relative entropy of these two states in terms of the sum of many conditional relative entropies for the sum over all possible sides of the lattice of these conditional relative entropies. But this just holds when the invariant state is a tensor product everywhere. And you can prove this, and this is a consequence, as Cambis mentioned before, is a consequence of strong subadditivity. And when you have this result, you can consider the global Lindbladian that is defined as the sum of local terms everywhere, and each one of these local terms is given by the difference between a channel and the identity. This channel is given by means, again, of the Petz recovery map for the partial trace in X, but it coincides in this case also with just sigma X tensor rho X in the complement because of this very particular case of sigma. So then the global Lindbladian applied to rho lambda is given by the sum of the difference of these terms. And for this very particular case, when you define a conditional log Sobolev constant, that is something that I mentioned before in the scheme, but we didn't define yet, is the same that the global log Sobolev constant, but the only difference is that now the entropy production here is just a local entropy production, and this is what you can see by this X here. And here, instead of the global relative entropy, we have a conditional relative entropy in X. So this is the definition of the conditional log Sobolev constant. And with this definition, in this particular setting, you can prove that the third part of the scheme mentioned before holds. So the conditional log Sobolev constant is positive and is independent of the system size. It's greater than or equal to 1/2. So putting this, which is the third part of the scheme mentioned before, putting this together with the result of quasi-factorization, that is the second part of the scheme mentioned before, and doing some algebra that I'm going to mention here, you get the positivity of the log Sobolev constant. You get that it's greater than or equal to 1/2. And in this case, the geometric recursive argument that I was mentioning before, in this case, is very simple. It's just what you can see here. So the idea is that you apply here the quasi-factorization for the relative entropy. For each one of them, you replace them by their definition, by the definition of the conditional log Sobolev constant. So you just bound dx by the quotient between the entropy production and the conditional log Sobolev constant. And now here, you just use that you can take the conditional log Sobolev constant out of this sum by taking the infimum over all of them. But we saw that all of them are lower bounded by 1/2. So this is the last step. This is where you use this lower bound by 1/2. And here you just use that the global Lindbladian was defined as the sum everywhere of all the local ones. And this is how you get that the quotient between the entropy production of the global system and the relative entropy is well, with a factor 2 because of the definition, is greater than or equal to 1/2. So in this case, it's quite simple, this geometric recursive argument, and it's basically because we don't have here the multiplicative error term that we have for the general case. If you have this multiplicative error term, it's much more complicated. Well, when you see this result, you can think of some open problems with which I'm going to conclude. So the first one of them is, okay, we have seen this scheme of tools to reach the positivity of the log Sobolev constant. Can we use the results that I presented in the first part of the talk to prove more interesting positivities of logs over constants. And well, this is the main open problem. And the idea is that, for example, for the heat by dynamics, with sigma being the Gibbs state of a commuting Hamiltonian, but not tensor product in general, Castoriano and Brandao proved that it has positive spectral gap. So it's reasonable to think that it might have logs over constant, because it would be an exponential improvement of the gap, but it's reasonable to think that it's possible to be true. So this is probably one of the main questions that can arise. The second problem is that, okay, I introduce a concept of a definition for a conditional relative entropy, but maybe you won't agree. Well, maybe you might think that there's a possible definition for this concept. So this is another possibility, this is another problem. And the third one is that we introduced two concepts during this talk, the conditional relative entropy and the conditional relative entropy by expectations. And both of them are very nice and have been widely studied in the literature. And maybe comparing both of them or characterizing where they coincide might be an interesting problem to work on. And many more things can arise from this topic. But this is mostly what I wanted to talk about. So for further knowledge, just check these two papers, and thank you very much.
Very much. Any questions?
Yes?
There is another open problem. We need to find some operational meaning of this condition.
Sure. Completely true. Yeah. So, thank you very much for pointing that out. Yeah, probably is the most interesting problem that arises from the introduction of the definition of conditional relative entropy, trying to provide an operational meaning for that. So yeah, completely true. Thank you. Yes?
Maybe this has also to do with the operational meaning, my question. But when you, maybe you can show the slide again with the properties. There was this property 2b right at the beginning, which was when it is exactly 0.
Sorry.
And
yes.
So in the previous slide to that, you had this 2-1 was a particular order of how you multiply operators. And I couldn't.
You mean here?
This one, the slide after that? Yes, this one.
Okay.
So you have this particular order. The rho AD is this sigma to the 1/2 AD and so on.
Yes.
So, I was in the past often fighting with the orders of these operators, and I couldn't quite see why it's clear that it should be that way, or where this comes from. Like, if you play with that, would that lead to a similar problem?
Yeah, no, it's not direct from the. So it doesn't come directly from the idea of trying to extend the conditional entropy in the case of the classical case or anything like that. It mostly comes from some recoverability properties that we want to impose in the part of the quasi-factorization of the entropy.
So you just know you want to have recoverability, and then it's natural.
Yes. Well, actually, I mean, it's somehow hidden, but the idea is that we want to use this quasi-factorization of the relative entropy to provide these log-Sobolev constants, and for that we have to define the conditional log-Sobolev constant, and then you are defining a quotient between. It's easier if I show it. Sorry. So here, when we define this conditional log-Sobolev constant, we are defining a quotient over this conditional entropy production and this conditional relative entropy. And the thing is that if you want this to be positive, at least every quotient has to be positive. So at least the kernels of numerator and denominator have to coincide. And we know the kernel of the numerator. So this is why we impose somehow that the kernel of the denominator coincides with. So that it just vanishes if and only if you have the conditions of the numerator.
Oh, this was essentially.
Yeah.
Okay.
So this is why I said that this is something that we mostly impose because of how we want to use that afterwards.
Okay.
Yeah. Yes.
Have you ever looked at this in probability? If they want to prove certain results, particular, having two algebras and moving it to another one, they call this a tangent construction. Have you ever looked at that?
Not really.
Closely related to this kind. Somehow you want to find another system which has more independence, and if you could do that at every point, then you could add it up, right?
Yes.
There's some in some instances that concept was successful. It's not always perfect, but some instances that worked.
Okay, so I should check that. Thank you.
Tangent construction is very famous.
Yeah, will do that. Thank you.
Questions? Let's thank the speaker again.
Thank you.